Welcome back. Today I'm going to talk about the Navier-Stokes equation. And the Navier-Stokes equation is essentially a balance or a conservation equation for the linear momentum of a fluid. And we will need it when we do casting or modeling for CVD and any applications of material processing that require motion of the fluid. So I have here from my notes the description of the procedure to derive the Navier-Stokes equation, and I wanted to go over some of the technical details so while you're reading it you would understand the approximations or the way that the equation just comes about at the end. So if you look here, you'll see that the linear momentum, we know that for a particle is the mass times the velocity. For a fluid volume element, if you have a volume d omega, then you have an amount of mass is rho times d omega. You multiply this by the velocity, you get an amount of linear momentum, and if it is integrated over the volume, you will get essentially the linear momentum. So the linear momentum is given by the integral over the volume of rho times v d omega. Notice here that v is a vector that we will consider. So the linear momentum also is a vector, and that's why it is in bold notation. And the conservation tells us that this quantity is a property of the material, just like the density, and it can be transported across an surface, and it is conserved because it's a conserved quantity because it's related to the density of the material, the density and its motion. So the conservation principle is very similar to what we've done in mass conservation. And in this case, if you remember, we have a rate of change of the conserved quantity, which is rho v, equals to the negative flux of the quantity leaving the surface. So this negative flux is right here, minus integral over the surface of the flux of momentum, which means that we're going to have to define what the flux of momentum is. And I'll do that in a second, and any source of momentum inside the material. And if you remember in the mass species conservation equation, we had a source of species that we called r dot triple prime for species I. That was if you have chemical reactions inside the material. But now we are concerned not with the mass, but we're concerned with the linear momentum. So the source for the linear momentum is the force on the volume element that we are studying. Now, what needs to be defined is the flux of momentum, because we knew that we have a drift flux of mass, which is the the density times the velocity. So if you remember, we have J mass, which is a vector, and the J mass was equal to the density, which is a scalar, times the velocity. So the velocity is a vector, so the flux is also a vector. Now, instead of having the density as a scalar, we're transporting not the density, but the momentum, which is rho times v. So we're going to define here JL, which is a quantity that describes the flux, and is basically transporting rho v with the velocity v. So you will see that the momentum flux has two vectors on the right-hand side, a v and another v. And when you have two vectors right next to each other like this is called dyadic, and the dyadic is 2, di is 2, so dyadic is a tensor, and the tensor is a second order tensor that is made up of the two vectors v and v. So it has the tensor, second order tensor, has 9 components, and if it's symmetric, it will have 6 components. That is unlike a vector, which has only 3 components in Cartesian space. So if we look at this now, we have defined the JL as equal to the density rho times the dyadic product of VV, which is, if you expand it, it will be a matrix. And if you expand it, it would look like this. So it would be, let's say you have V is like a vector here, which is Vx, Vy, and Vz. So Vy and Vz. And then you have another vector, which is Vx, Vy, Vz. When you take the dyadic product, this is called the outer product. You remember the inner product, you take the two vectors and you transpose one of them and you multiply element by element and you sum, then you get a scalar quantity. So the inner product gives you a scalar quantity. The outer product gives you a 3 by 3 matrix. So you will have a 3 by 3 matrix here that has the products Vx, 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 Vy, and so on. So you have a 3 by 3 matrix that you will have instead of the contraction. So instead of contraction, when you have a dot product, you have an expansion when you have a dyadic product to get a matrix of V times V. So having said that, we have now the JL is right here, and it's equal to rho times V, and we have now to consider the force. So the force term that remains here, and the force, this is the internal force. So the force on a fluid element is composed of 2 parts. One would be a body force inside the material, which is the force per unit volume. We can call this a B. B is the force per unit volume. So the total force on the fluid is going to be an integral of B over the entire volume. And the other one is that if the fluid has surfaces, like you're putting pressure from one side, when you're casting, you have some containing walls, putting other pressure, that is the surface traction, T. So T is a surface force. We call it traction. And the integration over the surface of T will give you the additional force on the fluid. So with that, we can now move on to describe the T. We know that T, if we have the traction from our mechanics background, the traction is equal to the dot product of the stress tensor and the normal vector, sigma dot n. So we would have the traction is equal to sigma dot n, and we introduce that, replace the traction with the sigma dot n, and therefore, which is right here, this is sigma dot n, and this is over the surface integral, and you change the surface integral to a volume integral by using the divergence theorem, or what we call Gauss's theorem. So we, instead of the now taking the divergence, you remember the Gauss theorem was for a vector, so the divergence of a vector over the volume. Now, instead of a vector, we have a tensor, but it applies the same way for a tensor. So you take the divergence of that tensor over the volume, and the result of the integral of T over the surface is the integral of the divergence of sigma over the volume. And therefore, we have now an expression that can give us the entire expression for the balance of linear momentum here is, as I have it here, let me move myself so you can see it, is that when we substitute back, then the balance of linear momentum is becoming now the equation that you see in here, and it shows us that we have now the balance of linear momentum. It has the first term is the rate of change inside the volume, and the second term is now the flux that was carried of the momentum on the surface. Now we're changing it to a volume integral using the divergence theorem, and now the traction is the force is decomposed into a body force inside the volume and the traction is now replaced with the divergence of the stress, again using the Gauss's theorem for a tensor in this case. So we have now a form for the momentum equation in an integral form, and we're going to manipulate it to show that some of these terms are going to drop out as a result of mass conservation, and the remaining will give us a weak form that can be localized, and we will get a strong form of the momentum equation or Navier-Stokes equation. So if we do that, then we see that we have, okay, let's just continue here. So if we do that, we see that the this term here, rho v, is retained. So rho v here, d by dt rho v, and then the divergence of the dyadic of the velocity times the density. We have the first times the divergence of the second plus the second times the derivative of the first. We use the chain rule. So we have v dot grad v, and grad v now is a tensor because grad is a vector and v is a vector. So you take the gradient of a vector, you get a tensor. So you have v dot grad v, and that is plus v d rho by dt, because we get it from the, we take the chain rule on the first term and we take the chain rule on the second term. So you get v d rho by dt plus v dot rho v, and that is integrated, all of these are integrated over the volume omega. On the right hand side, we haven't done anything yet. We only expanded, used the chain rule on rho v, the chain rule on rho vv to get this expression. Note that this term here is the material derivative, so it is rho capital D by dt of v. So this takes care of the, this is the material derivative. And then this second term, we have used it before. This is the total conservation of total mass, and therefore that is equal to 0. So this consequence of mass conservation, this term is going to drop out, and we have a 0. So this goes to 0, and now the weak form of the conservation of linear momentum is given as below here. Rho capital D by dt of v d omega is equal to the body force integrated over the volume plus the divergence of the stress integrated over the volume. So that's the statement of the conservation of the momentum. Now, the difficulty in here that remains is that we need to figure out how is the stress related to the velocity, because we have everything and we want to follow the velocity, and we want to follow the linear momentum, which is the same as the velocity in a way, but we got stuck with the stress. So the next step is to find a relationship between the stress and the velocity, or the displacement. You remember that the velocity is the time rate of change of the displacement. In mechanics, if we have a static solid, the stress is linearly related to the displacement. In a fluid, we have a similar relationship in which we have, it's called the Constitutive Equation, in which the velocity is linearly related to the stress. And with that, we can close the loop and we can substitute for sigma and get an expression for that actually allow us to compute the velocity field everywhere. And that's what we will do next. So if we have here, let's say in the next step, if you look at this equation here, this is what we have in the strong form, because the equation is valid for an arbitrary volume omega, and therefore the integrals can drop out, and now the equation is simply this one: rho d v by dt equals F. What is F? It's the total force on the volume of the fluid, and the total force is composed of a body force, such as a magnetic force, for example. If we're doing electromagnetic processing of material, we are adding heat through an electromagnetic current, for example, then you get MHD type forces, plus the divergence of the stress, which is the remaining obstacle in the Navier-Stokes equation. So now we're going to have to focus on the divergence of the stress. And the way that we're going to do it is that the stress, we're going to start from a constitutive equation. And the constitutive equation is that we start by saying that the strain rate in the fluid, which is strain rate, is similar to the strain. Remember, the strain in solids is the symmetric part of the displacement with respect to position vector. Here, the strain rate is the symmetric component of d, which is dvi by dxj plus dvj by dxi. So this is the strain rate, and the constitutive equation is that the strain rate is linearly proportional to the stress. That's the assumption, a basic assumption of fluid mechanics, similar to Young's law, for example, in solids. So we have here this relationship expressed as the stress tensor is equal to a constant tensor plus a fourth order tensor, Cijkl, times the strain rate tensor, EKL. And the reason is that when you have a second order tensor related to a second order tensor, then the relationship is via a fourth order tensor, so that you can sum over repeated indices. So the repeated indices here are the K and the L. You're summing over the K and L, and what remains, it will be the I and J on the left hand side. Okay, so if we take this relationship, this very general relationship, and know that under symmetric, under rotations and translations, then the relationship should not be dependent on rotation or translation. That's called a the tensor is an invariant to rotations and translations. If we have a tensor of that nature, that's called an isotropic tensor, and the tensor must be of that nature. So it will be, we're going to write it alpha ij as minus p, which is a constant to be determined, times the canonical delta function, delta ij, and delta ij is equal to either 0 or 1, and is 0 if I is not equal to j, and it's 1 if I is equal to j. So it's either 0 or 1. And also theCijkl has to be an isotropic tensor, and the isotropic tensor in fourth order is expressed, as you can see here, as a lambda times delta ij times delta kl. So this is the isotropic nature of fourth order tensor, plus mu times these combinations, delta ij, delta jl, plus delta il, delta jk. So this is kind of the forms that we have to kind of accept for isotropic second order tensor, and which is this, and fourth order tensor, which is that, if they are invariant to rotations and translations. So with that, we discover, if we just put that back here, then we substitute these equations, 39 and 40, into 38. So this is 38. This 38 is the assumed linear relationship between the tensors, and because of the invariance, then this assumed linear relationship must be of this form that you see here. So it should be of this form. The sigma ij is equal to minus p, which is an arbitrary constant now, which we'll see later that is going to be the pressure, plus 2 mu eij plus lambda delta ij ekk. And lambda mu are again arbitrary constants. In solids we call them Lami's constants, but here they are just constants in the problem that we will define in a minute. So if we just now define the P as the isotropic pressure, and the pressure is the trace of the stress tensor, 1/3 of the trace of stress tensor, negative of course because it's a compression by sign convention, then sigma ii equals minus 3p, and that should be equal to, we substitute j equals I in this equation as a, because it's an index equation, so we can replace one index at will. So if we just substitute on the left hand side I equals j, and the right hand side I equals j, we can get a solution. So let me just write it clearly. Substitute I equals j on left and right. Then on the left hand side you will have, instead of sigma ij, will be sigma ii, which we know if it means that it's the isotropic pressure. And on the left hand side you have minus 3p plus 2 mu eii plus 3 lambda ekk. And those are also the traces of ekk is the same as eii because it is the trace of the strain rate tensor. So with that, we have now, we must conclude that lambda must be equal to minus 2/3 of mu, and we can now plug it back to get the relationship which we've been trying to establish between the stress and the strain rate, or the velocity gradients. And that relationship is what you see here. So at this point, we are going to define mu, which is an arbitrary constant, as the coefficient of viscosity. And that's the first time that it appears here in the Navier-Stokes equation. and the stresses due to the viscosity, we're going to separate them. And so you have here pressure stress, this is pressure stress, and these two terms together are associated with the stress as a result of fluid viscosity. We're going to call this stress related to the fluid viscosity as Qij for simplicity. So we will have sigma ij is composed of the pressure stress P times delta ij, and then the Qij. So if we know that Eij is this term, one half of this term. And same thing for EKK is this term here. So you would have now the linear relationship that we are trying to establish between the stress and the velocity is complete, essentially complete for the isotropic fluid. So sigma ij is equal to minus P delta ij plus mu, and you can read the rest here showing you the relationship between the stress and the velocity gradients or the strain rate. So we're in a position to deal with the divergence of sigma that was remaining in the formulation. So we're going to take the sigma ij and put it as in the divergence term for j, for the stress sigma on the right hand side. And the divergence is going to be this entire term. Divergence now is written in index form. So remember where we ended up with this kind of innocent form of Navier-Stokes equation, which is actually this form here. So this is the innocent form of Navier-Stokes equation. The term that took us so long is the divergence of sigma. And the divergence of sigma, we had to start with a linear relationship between the stress and the strain rate, or the velocity gradient, and then argue that you have invariance under rotation and translations to obtain isotropic tensors, the delta ij and the for the pressure, and then another tensor, isotropic tensor for that's associated with the viscosity, and then we obtained a special form, which is now this linear relationship, and that is ready now to be introduced in a divergence. And the divergence means you take the derivative with respect to the j component or xi component. So you take the same expression and you just write it like here, where you have instead the pressure, you take the derivative with respect to xi, and the rest you have xj, as you can see in here. So this is eventually the divergence term that we have. And you can show that the last parts of this expression here, these terms in here, will become you can pull the mu out if the viscosity is constant, which is a good assumption. Doesn't depend on space because the fluid is very well mixed. Then you can pull it out from the derivatives, and then you add up, you get the Laplacian of the velocity. And that is now giving us an equation that can be written in a more compact form that we have in here. And this compact form is telling us that, let me highlight it here. And this form is telling us that the density times the material derivative of the velocity, so this is the form of the momentum transport, is equal to the local forces. And the local forces are three. One is a body force, one is a pressure force, negative the gradient of the pressure. If the pressure is equal, then the fluid is not going to have a force on it. But if you have a gradient in the pressure, then the fluid is going to move. Just like the Bernoulli equation, the fluid moves as a result of pressure differential. This is minus gradient of the pressure. And then the only additional term that we have here is the viscosity times the Laplacian of the velocity. And that constitutes the very well-known Navier-Stokes equation that we will be able to solve also in any material processing simulation in the future. And with that, I think we're going to stop at this point. See you in the next lecture.